In this lecture, we're going to talk about the most popular learning algorithm called gradient descent algorithm, which is the backbone for the backpropagation algorithm, which is to be used by the artificial neural net or deep learning models, which have become so famous these days, and as they will be covered in the next couple of weeks. So the gradient descent learning algorithm essentially enables computing the posterior probability directly. Hence, the discriminative learning algorithm model is possible. So in this lecture, what we're going to do is essentially introduce the concept of the gradient descent learning algorithm by means of using linear regression as an example. So this becomes essentially the discriminative learning as opposed to the generative learning model, which we have talked about back in when we talked about the Bayesian learning algorithm. So we're going to use, once again, linear regression using a single variable as well as multiple variables, just to be able to introduce the concept of the gradient descent algorithm as a discriminative learning algorithm. And as a follow-up of this material is going to be the logistics regression, which is going to be the expansion of this logistic regression is essentially the artificial neural net model. And we can also talk about the concept of regularization when you have an overfitting problem. So these are the follow-ups as in lecture 7. So the motivation for the discriminative learning is that back in the Bayesian learning lecture, we showed how to build classifiers when the underlying densities were known. We talked about, for example, the Bayesian decision theory being, for example, identifying the discriminant function. And then we essentially compared the two discriminant functions, wherein each of the discriminant function is essentially a posterior probability density. For example, here, just to bring you a memory, as we recall that this was the input of input data samples. And then they go into these discriminant functions, where each of the discriminant functions essentially would be represented by the posterior probability. So what we do is that essentially we select the maximum of these discriminant functions as the class assignment. In order to perform the Bayesian learning, if you can recall, what we did was that we essentially had to estimate the posterior probability by means of the likelihood as well as that of the prior probability. For example, what is most important is this, which is the likelihood, where this was actually estimated by means of the parameter estimation. For example, typically if you have data set that consists of the positive and the negative, what we did was that we essentially try to identify the density function of this, which is the likelihood, by means of, say, X, all the data samples being, say, fitting to some Gaussian model with the mean and the covariance, where these two parameters were estimated. And similarly, we do the same for, say, that of the negative class. So this makes it as a generative approach because the likelihood and the prior were essentially, especially the likelihood, were estimated based on the data samples. There are other means also of estimating the likelihood, including that of the non-parametric density estimations and so forth. So one of the advantages of being able to do this, once you were able to obtain, say, the likelihood, is that you can then generate new data samples based on the likelihood. In other words, once the likelihood function is established, then what it means is that you can actually generate data samples using such a model. On the other hand, the discriminative learning model, which we are going to be handling here in this lecture, is that we try to obtain and find the posterior probability directly. In other words, by means of either explicitly or implicitly, we try to obtain the posterior probability or distribution directly. And such means is done by, for example, SVM, where in the SVM, we try to obtain the decision hyperplane by means of obtaining the support vectors. And similarly, we are going to talk about artificial neural net. This is another very good example of a discriminative learning, where once again, all we have to do is to obtain the decision boundary by using the artificial neural network framework. So that becomes a discriminative learning, because here in the ANN as well as SVM, we don't really have to delve into obtaining the likelihood function itself. Similarly, the reason why we are learning the discriminative learning is that rather than going through the generative learning model, we try to obtain the decision boundary directly by obtaining this posterior probability. And the mechanism that will allow us to be able to do so is the gradient descent algorithm, which we're going to talk about here in this lecture. Just before delving into the gradient descent with an example, is that for the discriminative learning model, here we don't really care about how the data is generated. All we care is about the posterior probability. And we can do that by directly obtaining the decision boundary that can separate, say, those of the positive and the negative. On the other hand, for the generative model, which describes how data is generated using the probabilistic models, the posterior probability essentially predicts the probability of y given x by calculating the joint probability, where this joint probability, as you know, is equal to the likelihood multiplied by the prior. So usually this likelihood is essentially estimated by means of estimating the parameters. For example, typically, let's say x being Gaussian with, once again, mu and say covariance matrix, where these two elements or these two parameters are typically estimated based on the sampled data. So here, the discriminative model is that it's going to allow us to be able to actually directly obtain this decision boundary by means of a certain algorithm called gradient descent. Now, of course, there are advantages of using the discriminative learning models. It's going to be much easier to learn and compute them than that of the generative model, because for the generative model, you need all the samples, and then using the samples, you need to come up with an estimation of the distribution, which is going to be pretty challenging to be able to do so, especially if you have multi-feature. And the data sample is very huge. On the other hand, the discriminant model also does have certain challenges that because of the fact that it's not a generative model, it does have the limitations in the modeling capability, especially, for example, new data cannot be generated with the discriminative model. And to be able to actually come up with a nice working decision boundary, which is this posterior probability, is that you need to have both the positive and the negative training set. And also, it becomes very sensitive to small size of the training data. So this is only good for when you have very large training value. For example, the reason why deep learning, which is a very typical discriminative model, is that it does require a huge amount of the training data set. So with that, you could actually overcome the overfitting problem, which is the problem for the discriminative model. So with that, let's now delve into the gradient descent algorithm by means of the linear regression as an example. So what's a linear regression problem? So here we want to simplify the linear regression problem by using just a single feature, one variable. So here we have a data set. Here on the horizontal axis is the size of the housing, and the vertical axis is the price. And so these are the axes represents those of the samples that we have collected. For example, a particular size of the housing that were collected out of the sample data is that for this particular size, let's say 1,500 square feet is roughly about $500,000. So this is, let's say we have a collection of about 50 data samples, and each of the data samples has the corresponding size as well as its corresponding price. So this would be actually good for a supervised learning, and the objective of this supervised learning for the regression problem is to be able to obtain its representative line or nonlinear line that represents the data set. For example, here, in this case, if we make an assumption that, say, the size of the housing versus that of the price is linearly related, then what we do is that we essentially assume a hypothesis model, so as a straight line, so we can actually predict, given a specific size of the data, of the size of the, say, housing, we can predict its price. Now, this is going to require, as you can see, a set of the data set with a pair relationship. So here on the left-hand column represents the size of the housing, and the right-hand side column represents the corresponding pricing. So once again, the horizontal axis would be the size in housing, and the vertical axis represents the corresponding price. And we have, let's say, for this supervised learning, we have n number of training samples, and the input variable is represented by this. So this would be the ith training sample, where each of these sample would have m number of features. But here, in this case, we only have x being a single feature because we have just the size of the housing as on the horizontal axis. So it's just one variable, and the output is also the price of the housing. It is also scalar, which is the target variable. So given the training set, all these data set, what we do is that by using a learning algorithm, we devise a prediction model, and this prediction model is usually done by certain hypotheses. So the hypothesis, for example, here is that this is going to be a straight line. So that this straight line assumption as an hypothesis is going to be used to represent this particular line, where the line, for example, if this is a straight line, would be then represented as, say, sum of two terms, where the first term represents the zero crossing or intersection at the vertical axis, whereas for theta 1, it represents the slope of this particular line. For example, the slope theta 1 would be the change in the vertical axis as per the change in the horizontal axis, say delta x. So this is the line representation, a straight line representation, which is the hypothesis that we can make for making the prediction. And so the learning model, essentially what it will do is to perform the learning such that theta 0 and theta 1 can be estimated, so that the prediction here can be as accurate as possible, which meaning that the straight line then represents these collections of the sample data nicely and very much accurately, as that this hypothesis function then becomes the prediction. So after the learning is complete, then once again, any size of the housing given as an input, then this learned model should be able to provide the estimated price as its prediction. So once again, what we want to do is, the very first thing that you need to do is that given the data samples like this, the X and Y, what you should do is to make a certain hypothesis. So here the hypothesis is, once again, is a straight line, where the straight line, once again, can be represented by a sum of two terms. The first term is the intersection of this line that crosses on the vertical axis. So this is the intersection that crosses the vertical axis. And then you have theta 1, which is the slope of the line, where the slope of the line, as you can see, is, if this is the change in the vertical axis as per the change in the horizontal axis, that would be the ratio of delta y over that of delta x. So these are the two parameters that's going to be required to accurately represent this straight line, which then should be able to represent all of the data set that's given here in the training set. Let's make a couple of observations here before we pursue any further. That is, if you have, for example, these two parameters, theta 0 and theta 1, let's look at a couple of combinations of these two parameters. For example, the first one here is the one with theta 0 being 1.5 and theta 1 being equal to 0, which means that if theta 1 is 0, that means that this is essentially theta 0, which is 1.5. So this is just a flat line looking like that. In other words, the slope is 0, right? 0 slope. On the other hand, for the second one here, this is when you have theta, h of theta of x being, say, 0.5x, because theta 0 is equal to 0. So this means that the zero crossing or the intersection takes place at 0. So the intersection takes here at 0 on the vertical axis, and the slope is that it's 0.5. In other words, 0.5 rise versus 1 for the changes in the x direction. And similarly for this means that now the intersection takes place at 1, and once again the slope is also 0.5, right? So we have this situation. So you can see that depending on what the value of theta 0 and theta 1 is, you can have a variety of a straight line. Now let's look at an example here with say a very simplified example with just 3 data sets. Okay, so we have just 3 samples which are indicated by these red crosses. So out of the red crosses, what we want to do is that we come up with an hypothesis that represents these samples as a straight line. So the straight line is going to be modeled with, once again, having these 2 parameters, theta 0 and theta 1. But let's just assume, just for the sake of simplicity, that theta 0 is equal to, say, 0, because here, as you can see, we have 3 possible scenarios of the parameter setup. Say number 1, number 2, and number 3. In each of the 3 cases, they all intersects at 0. So we're going to just assume theta 0 is equal to 0. And each case, therefore, the change of the line is going to be done by having a different slope. For example, we can have slope being, say, the case of 1. So theta 1 in that case is equal to 1. So the slope is equal to 1 and 1 here. And for the second one here, for theta 1, this is going to be equal to 0.5 and 1. So this is equal to 0.5. The slope is 0.5. And the third one here, as you can see, it's lying flat on the horizontal axis. So obviously the slope theta 1 is equal to 0 here. Okay, so 3 different possible scenarios of a straight line modeled by this hypothesis function. So in that case, out of the 3, what we want to do is then measure how well we did in terms of making the good hypothesis. That is, out of these 3 lines, 3 hypothesis lines, which one is the one that actually best fits to the data samples. So the way we're going to do that is by means of this cost function representation. And that cost function representation is done by this J function, where the J function, which is function of the parameters theta 0 and theta 1, is essentially the MSE, mean square error, which is the sum of all the samples of the errors, the square of the errors, between the prediction to that of the real sampled output Y. Meaning that, for example, if we have, let's say, because we have 3 data samples, here's 1, 2, and 3 data samples, we then also have, once again, 3 possible scenarios of the hypothesis function. So let's just do that, for example, one with, say, number 3. Okay, so let's do that with this one here. So using this as our hypothesis, number 3. So that means that for each of the output, or the each of the possible output is that for the hypothesis, it's actually they're all going to be the output of the hypothesis for each of the sample being, say, here, here, and here, is that they're all 0, right? But the actual value of the sample being at each of these locations of the x is that you have 1 being at here, which is 1, and the second one being at 2, and the third being at 3, which means that we essentially have an error between this guy and this one here. And we also have the error between here, the real sample, versus that of the, say, hypothesis, the prediction, and also the error between the real data versus that of the hypothesis or the prediction. So we have sum of the squares of the errors. So we have the error here, another error here, and error here. So we square each of the error, and then we sum them up all together, because we have 3 samples, so n is equal to 3. And then we divide by n, which is actually the average of the error, or the average of the squared errors. We also divide by 2 here. Now this 2 is just it's just there for the sake of the mathematical convenience, and it doesn't really affect what we are trying to do here. That is, what we are trying to do here is to identify the theta 0 and theta 1 such that this cost function becomes minimized. In other words, let's just move, let's say, for example, for the second one here. So for the second, say, for the second hypothesis, by going through exactly the same process here, then we have this much of an error, and this much of an error, and this much of an error, and then we square the error, which is the difference. And once again, we square and then sum all these errors, and then we divide by, say, n, which is 3. So we essentially divide by 6, right? 2 times 3, right? So then it's going to actually give you some value. So that value, by the way, happens to be right here. Going back to, say, 3 here, by the way, because it's the one that has, out of the 3 possible scenarios of the straight line, gives you the maximum, or the one with the highest amount of the error square, or sum of the error square. So it's actually right here. compared to, say, for example, number 1. Okay, so in the case of the number 1, as you can see, the prediction or the hypothesis model to that of the actual data is actually 0. So the overall error here is actually 0. So here in this case, number 1, you have a 0, say this particular location being at 0. And so in the case of, say, theta 1, with an assumption that theta 0 is equal to 1, so the function, the j here, is going to be only a function of one variable, which is theta 1. So we've done that for obtaining or plotting j as a function of theta 1 for 3 cases, one here, one there, and one there. And we can also do the same for the positive values of the theta 1. That is, we move, say, theta 1 here to the right of, say, being 1, which means that the slope now is going to be above this one, right? Above this one. So, for example, we can have this much as well as this much of the hypothesis. So we can have a couple more hypotheses here, and as you can see by plotting everything, the cost function as a function of the theta 1 is that there's a nicely plotted symmetric, as you can see, looking symmetric, very much symmetric, bowl-shaped error function that you can establish. So with that, as you can see, we can actually identify the lowest point of this error function, and the location where the lowest error function is indicated represents the theta 1 star, which is the one that's going to attain with the minimum value of the error function. So this is the term that we need to obtain, that is to minimizing. So by minimize, so what essentially, which parameter, what of the values of the parameter that minimizes cost function? So here in this case, in our example, the theta 1 that minimizes this error function is equal to, say, 1, right? That's the one that minimizes the error function. So just to summarize what we have said so far is that we have this cost function where the cost function is going to be used to be, and then it's going to be minimized with respect to the parameters theta 0 and theta 1. And before that, we need to come up with, say, some guessing as to how the data here, the data samples are essentially situated. So here in our hypothesis, we're going to make an assumption that it's a straight line. So for the straight line, there are 2 parameters, theta 0 and theta 1, that needs to be identified. And so the way we are going to identify theta 0 and theta 1 is by devising a cost function, which is essentially an MSE, mean square error. So what this mean square error says is that what you do is that there is a prediction made by this hypothesis, and then you subtract off by the samples corresponding, say, axis, the y-axis, and then that becomes essentially the error. So you square the error, and then you sum of all the sample values, right? So you have there are 3 samples, so you need to sum 3 of these samples, and then you divide by the total number of samples, which once again, in this case, be equal to 3, and we further divide by 2, where this 2 is there, once again, for the pure reason of mathematical convenience. So this is going to be actually canceled out anyway later on. So the goal here is to, once again, by minimizing, what are the theta 0 and theta 1 that minimizes cost function? And so we need to then obtain, we can then obtain theta 0 and theta 1 by which represents the parameter that we are trying to use for the best hypothesis, and therefore be able to use that as producing the best prediction. So here in our case, we assumed that theta 0 is equal to 0. So only thing that we had to do was that this 2-term representation is going to become simplified with a one-term function, where that one-term function only has then one particular parameter theta 1, and then it goes through once again through the cost function. And then what we want to do is to obtain or find theta 1 that minimizes this cost function. Okay, so there are many possibilities of this straight line in the case of the data sets that we have. For example, we can start off with let's say assume that this red is the final answer with the such that with the specific values of theta 1 and theta 0, that it represents the best estimate or the best prediction using these training samples. Prediction of a straight line. So the question is, how do we go about doing that? How do we go about obtaining and searching for the parameters theta 0 and theta 1? So what you do here is that you essentially start with some initial value, theta 0 and theta 1. So that initial value, for example, could be this. So let's say this is the theta, say we have theta 0 as well as theta 1, which is what we need to obtain, which is represented by this particular red straight line. Whereas here, for this one here, could be one with some initial value. And we can also plot the cost function. Here in the cost function plot, this is done in 2 dimensions, say theta 0 as well as theta 1. So this is theta 0 and theta 1. And as you can see, it's a very much symmetric and smooth surface that has that indicates the global minimum here. So we can start with some initial value, which is at some random locations of theta 0 and theta 1. And then by using certain learning model, and that learning model, once again, is called gradient descent, should be able to then search for the global minimum as the iteration takes place. And it is done, once again, by means of this vehicle called cost function, where the cost function is a function of the parameters theta 0 and theta 1. And the idea or the goal here is, once again, is what are the theta 0 and theta 1 that minimizes this cost function? In other words, what is the global minimum? Where is this global minimum? So the global minimum should be the theta 0 star and theta 1 star. So this is what we are seeking. And we're going to be able to do that by means of the gradient descent learning algorithm. So how do we do this? What is the gradient descent learning algorithm? So here, once again, the important element that composes the gradient descent learning algorithm is that we need to have a certain cost function that needs to be defined. And what we want to do is to minimize this cost function in terms of the theta 0 and theta 1. Those are the parameters. So the outline is that we start off with some initial guessings of theta 0 and theta 1, and then we keep changing the values of theta 0 and theta 1 to reduce the cost function until hopefully we end up at a minimum. So the question is, how do we keep changing this theta 0 and theta 1? And further then, once again, it arrives to the global minimum. So here's a decision, here's the cost function surface. As you can see, it's pretty rough in the sense that there is a global minimum right here, theta 0 star and theta 1 star. But at the same time, there's other minimum here, which is not the global minimum. Let me just say that that's theta 0 and theta 1, which is called a local minimum. Meaning that the level of the cost at the local minimum is actually greater than that of the global minimum. Now, the reason why the local minimum here is actually plotted is that being able to reach toward the global minimum is actually pretty challenging, because depending on where that initial point happens to be, if the initial point happens to be here, then the search process will take you to the global minimum. On the other hand, suppose that your initial point happens to be here, then it's going to actually search and then pretty much stuck at this local minimum. So the initial point actually becomes very, very influential. At the same time, what kind of cost functions that you will have? The cost function that's going to have with this, as you can see, very rough surface, not a smooth surface. But when I say rough surface or not smooth surface, is that that it could have these local minimum points. So if this is the case, then the problem becomes very complicated. On the other hand, for the linear regression problem, which is the one that we're trying to solve, actually is a convex problem. So therefore, the global minimum is actually guaranteed. In other words, you're not going to have the local minimum. We're going to talk about this convex type of problem later on. But here, once again, for the linear regression problem, fortunately, we're not going to end up having any of the local minimum problem. Now, even though, by the way, even if the this cost function is very rough, in other words, not very smooth, having these local type of minima, then artificial neural net or deep learning model essentially solves that kind of problem. In other words, it does overcome those of the local minimum problem nicely. So that's why all of these gradient descent learning is going to actually head toward the direction of artificial neural net type of model as well as deep learning model, because once again, the local minimum problem will actually be resolved by having a multiple, hidden units, which is going to be the framework for the artificial neural net, which is a little bit more complicated than the type of model that I'm showing here today. Here, all I'm trying to say is that we need to build the learning model from that of the gradient descent on a very simplified format or form, which is essentially a linear regression problem. Okay, so as I said, having these two different possible initial values, you could end up having a global minimum or a local minimum. Okay, so what is this gradient descent algorithm? So the gradient descent algorithm essentially is represented by means of this particular very simple algorithm, that is that we repeat the process of this iteration, which is an updating rule until convergence. And this updating rule essentially is this, right? Theta j becomes the original theta j plus the changes in the theta j. So this change in the theta j is done by the minus alpha times the gradient of the cost function. In other words, this is essentially is the negative of the alpha times the gradient of the cost function with respect to each of the parameter. So this is very simple algorithm, the gradient descent. The gradient is to take the partial derivative of the cost function with respect to the parameter, and descent means that you in fact just place this negative sign so that if this is just one dimension, say theta I, and let's say this is the cost function with respect to say theta I, as the cost function, So in this case, what we are trying to do is look for this theta I star. So this is the direction that we are trying to do by making a certain initial value. So at initial value here, as you can see, if you have a positive, say, gradient, say dj, d theta, this is going to say the vector is going to sort of point positive direction. But here, what we want to do is actually go backward toward where the lower value is, right? So therefore, we've in place a negative sign there. If the initial point happens to be somewhere here, and we do the same, dj, say, d theta, then the direction is positive already. So with the negative sign there, because it's a negative sign there, and then this is actually the negative direction because it's actually going down, the direction of the arrow is. So therefore, the change of the theta then actually is going this way, whereas this one here is pointing this way, all toward where the minimum point is. So that's why we have this word called the gradient descent. Descent meaning that it continuously lowers the value of this decision of this cost function j. So in terms of applying or implementing this iteration, is that we have to do a simultaneous update for, say, two parameter case, meaning that for theta 0 and theta 1, we have to actually update these two parameters together simultaneously. So the correct procedure is that when we do this gradient descent, that is to take the negative and alpha times taking the partial derivative with respect to theta 0, this is done first, and at the same time we do exactly using the same the j function, the cost function. We take the partial derivative of this j with respect to theta 1 and then multiply that by minus alpha, and that's added to the previous value of theta 1. Now what is incorrect is that we do this asynchronously. That is, you do the update of, say, theta 1, say theta 0 first, and then incorporating the theta 0, we put that here to obtain the cost function with theta 0 in there, which is the updated version. And then, sorry, actually theta 0 is this one here, right? Right, so theta 0 is there. Right, so theta 0 is plugged in here, then use the partial derivative with respect to theta 1. This actually is an incorrect procedure because you're not actually taking the partial derivative simultaneous, both theta 0 and theta 1 together. So this is the correct procedure. Okay, so here what is also important is this alpha. When you do this updating process of the gradient descent, is that this alpha is the learning rate, which essentially defines the amount of the steps that it takes. It could be very, very large step or very, very small step, depending on the situation. Let's say that if alpha is just too small, then the gradient descent is going to be pretty slow. In other words, let's say the initial point happens to be right here, and we are trying to go here, which is the global minimum. But if the step that it takes is very small, if it's very small, then once again, it's going to move toward the global minimum, but how long it takes is going to be pretty slow. On the other hand, if alpha is too large, which is the other extreme, is that the gradient descent can actually overshoot the minimum. In other words, say the initial point happens to be here, we actually want to move to here because this is the global minimum. But if the alpha is just too small, it could actually overshoot and in fact become diverge rather than converge. So what I'm trying to say is that alpha needs to be sufficiently small, but not too small. Okay, so it has to be just about right. So how do we then obtain alpha? Well, a typical value of alpha would be, say, 0.1. Okay, so if it is like, say, 0.0001, just too small. So this would be a good starting value of the alpha. But of course, I mean, to be able to accurately obtain alpha is that you just have to go through a lot of trial and errors. But typically, you don't want it to be just too small or alpha being just too large. So 0.1 is typically about a good size. Now, here we want to apply, say, the gradient descent algorithm on a very rough surface. In other words, not like a smooth surface looking like that, but suppose you have the cost error function looking like this, where here, obviously, where on the right-hand side having a global minimum, which is guaranteed because it's got the smooth error surface. We have pretty much a rough surface here in this example. So therefore, you have the local minima, okay? Whereas this one here, for example, is the global minimum point. And this is where we want to go. But suppose our initial say starting point happens to be here. This is not going to jump into here. It's actually going to go toward once again by using the negative of the gradient or the gradient descent is that this is going to actually look for this guy rather than go over to the other side. So in that case, the gradient descent can converge to a local minimum, even with the learning rate alpha being fixed. So alpha, for example, is actually in this case is become pretty much independent because once again the error surface is very, very rough. And on the other hand, let's just talk about, for example, the two cases here. So when we have a convex say error surface situation, which means that error surface looks something like that, which means that if you have like two particular point here that touches the say error surface, and if you connect the 2 points in a straight line, then it actually the straight line belongs to say one particular area. Okay, so if you have a situation where the cost function looks something like that, with say two randomly identified points on the error surface, then we say that this error surface is being convex. On the other hand, if we have an error surface that looks like this, any particular say point here, these two are the 2 points on the error surface, and if you connect these 2 points together, then as you can see, it obviously passes through 2 different regions. The one with, say, red, as well as, say, let's say, green. So you have 2 possible regions, the green and the red. And as you can see, these 2 points, and if you connect these 2 points together, obviously it crosses both the red region as well as the green region. So that makes this particular cost function as non-convex. So if it is a non-convex error surface, then obviously it's going to have a local minima, whereas for the any of the error functions having a convex structure that looks like this, the global minimum is actually pretty much guaranteed because it's a smooth surface. Okay, so how do we then actually implement the gradient descent algorithm? So here, once again, the gradient descent algorithm to be performed over the linear regression model is that for the gradient descent, we have this repetition of the updating process, which is this. That is, the previous value of the parameter is updated by taking the gradient descent, that is, by taking the partial derivative or the gradient of the cost function with a negative sign in front, and then you multiply by some small size of the step. So this much is actually added or is to be modified. So you can kind of consider that as delta of theta, say j. So theta j, once again, is sum of the previous value plus the change of the parameter value of theta j. So this is repeated until converges. When we say converges, I mean the previous value of the theta j and the updated value of theta j, the difference is very, very small. So what we want to do is to apply the gradient descent algorithm onto a linear regression problem, linear regression model. So the way we will do that is, once again, assuming with the assumption that the data set is going to be represented in a straight line, having these two parameters, theta 0 and theta 1. What we're going to do is to put this prediction into this cost function model. So this is the cost function model, which is the 1 over 2n times the sum of the squares of this regression model, and then you subtract off by the corresponding output y sub I. So this is the one with the input, and this is the one with the output, where this is the prediction based on the input. So the idea here is that now that we have the linear regression model invoked into this cost function, is that we need to then obtain this gradient of the cost function with respect to each of the, say, parameters, say theta 0, as well as 1, theta 1, and then do the same for, say, theta 1. Okay, so when we do that, when we do this, taking the partial derivative with respect to, say, theta 0, as well as so this is for theta 1, theta 0, because we have theta 0 minus alpha times say dj d theta 0, and we also do the same for, say, theta 1. So this is going to be theta 1 minus alpha dj theta 0 theta 1 d theta 1. So given, once again, for j, theta 0 theta 1, as you can recall, is equal to 1 over 2n sum of all the squares of the difference between the hypotheses subtracted of its corresponding output, and we square, so the I can be say n number of the data points, right? So when we take the derivative of this function with respect to, say, theta 0 and theta 1, the theta 0 happens to be just this, right? Because when you take the derivative of this with respect to, say, well, because hypothesis function here is that this hypothesis function is essentially theta 0 plus theta 1 xi, right? So this is the hypothesis function right there. So when you take the derivative of this j, the cost function with respect to theta 0, it's going to be, well, the square is going to come over to this side, so that actually cancels off this 2 here. And then we take the derivative of this with respect to theta 0, so it's going to be just 1. So this is going to be just multiplied by 1. Whereas for theta 1, when we do this with respect to, when you take the derivative, partial derivative of the cost function with respect to, say, theta 1, then on the right-hand side, it's exactly the same process as this, But on the right-hand side, because we now are taking the derivative of the second term, which with respect to, say, theta 1, so what is going to be left would be x sub I, so which is what we have, x sub I. Okay, so we now have the update rule for the convergence for both theta 0 and theta 1, because we have two parameters, and we do this update simultaneously. Okay, so once again, what we do is that we can do some initial guess, say initial guess here, because this is a convex function. Once again, a global minimum is essentially guaranteed because it's a smooth cost function. So what we do is that we sort of, once again, do an initial guess. So let's just say that theta 0 is 50 and theta 1 is 0.06. So say somewhere here, okay? And then by using the gradient descent algorithm, which we just talked about, that is to update for, say, theta 0, as well as you have the update rule for theta 1, because, so theta 0 is theta 0, say, plus delta theta 0, and so forth. And theta 1 is similar, right? Theta 1 plus delta theta 1. So this is repeated by performing the update process. So essentially what we are trying to do is to search for the parameters theta 0 and theta 1 that minimizes this cost function, which is right here. So this is the theta 0 star and theta 1 star that we are looking for. And once that is arrived, then this one here, which is delta y versus delta, say, x, then that would be theta 1, which is the ratio between delta y over, say, delta x, and the intersection here represents the theta 0. So this is actually theta 1 star and theta 1 star. And so we start off with some initial guesses, say 50 and 0.06. Continuously, we can then plot the, say, the cost function for each of these guesses. In this new guessings of theta 0 and theta 1, which is going to be essentially this, then it's going to give you the cost function being at this particular location. And now the thing is, by the way, what essentially does is this gradient descent is that because it's this is actually two-dimensional, theta 0 versus theta 1, what it does is that it looks for the perpendicular direction toward toward the descent direction. That is, once again, what is the perpendicular direction? So if you are at this location, the perpendicular direction of this particular, let's say, ellipse is that it's sort of like going this way, right? So if you are here, then I guess swings a little bit. It changes, and then so gradually it's going to go like this. So toward the global minimum. So what I'm saying is that given any of the initial point, right, let's say right here, then what it tries to do is to look for the perpendicular direction. So here in this particular region, location, the perpendicular direction as far as this particular, say, ellipse is that this is actually going this way, right? Is the perpendicular direction. So this is going to go sort of like going this way, right? Given that, say, this as the initial point. Okay, so we continuously update theta 0 and theta 1. So the next dotted point as this gradient descent becomes updated is right here. And then further, it's right here. So we can see that the process of updating will lead you toward the global minimum, which is right here. So finally, the update rule says that this is going to be going toward the global minimum. And right here is where the global minimum is located. So once you obtain, say, theta 0 star as well as theta 1 star, this is going to be, this is pretty much says that it is converged, meaning that the changes of the theta 0 as well as theta 1 at this particular location is going to be very, very minimal, or the change is actually virtually zero. So we say that this location here is that it is now converged as far as the update is concerned. Okay, so far we sort of introduced the concept of the gradient descent algorithm using linear regression with a very, very, the most simplified version, right? Just using a single variable. What if we have now multiple features? Okay, so multiple features. So before we had a single feature case. In other words, we just had the size of the housing versus that of the housing price. So we were able to actually model this process, a straight line, using a two-term hypothesis function looking like that. But what now if we have multiple features? In other words, we now not only have the size of the housing, but say the number of the bedrooms, the number of the floors, or the age of the home. Compared, for example, that all of these four features versus that of the housing price. So this means that we now have the multiple feature case. And as before, let's just say that n is the number of samples. M would be, in this case, the number of features, because before we only had just one feature, one variable. Now here, m, in this case, would be equal to 4. Okay? And similarly as before, we had x sub I, which represents the input of the ith training sample. With the bold-faced x2 represents that it's now it's got a multiple feature, so it's a vector. And actually, this should have been, say, so let's say, so this then would be the value of the feature j, in the ith training sample. In other words, let's say x sub I would be a vector, which would be this, then would consist of, say, x1 of I, x2 of I, and so forth. So there are, if you have, say, m number of features, you would have this type of representation for the feature. So previously, with just a single variable, one feature case, we only had a straight line case looking like that. But for the multiple feature case, the hypothesis function, now it's going to be an expanded version. And as you can see, now you have, say, x1, x2, x3, and x4, where each of these represents different type of features. So for example, the hypothesis function now is going to be a sum of, say, theta 0, which is that constant that crosses the intersection of the vertical axis, as well as other terms, where all the other terms would be simply looking like this. That is the product between the parameter as well as the feature value. And we have, once again, four types of features, x1, x2, x3, and x4. Now, this is still, by the way, considered as a linear regression, because, as you can see, each of these features is just multiplied linearly by the parameters, theta 1, theta 2, and theta 3, and theta 4. So that means that you have essentially these parameters as some sort of weight associated by each of these feature, say x1, x2, x3, and x4. So to be able, so the parameters represents the weight. So weight that tells you about what should be the prediction value, as once again having these weights found, determined, then having these specific feature values as an input, then the prediction can be calculated. Okay, so once again, the multi-variate or the multi-feature case for the linear regression, the model representation is this. So for the convenience of notation, let's just define, for the whole thing, we might as well put, like, say x0 there, just to be aligned with the rest of the terms. Let's just say that x0 in this case is equal to, say, 1, so that we can actually represent this prediction model or this hypothesis. So once again, for the convenience of notation, x, which is the boldface, is an m vector, the m-dimensional vector. Well, actually, it's m plus 1-dimensional vector, because x0 is yet another element, another entry, where that entry happens to be always equal to 1. On the other hand, because we're multiplying each of these parameters, or the input feature, to that of the, say, parameters, so the parameter also has to be having exactly same dimensional space, m plus 1. So this means that the hypothesis function actually can be expressed very, very simply or easily, which is essentially a dot product between, say, theta, which is this, the parameter, to that of the input feature. So this is just once again, this is essentially, say, theta vector dotted with, say, x vector, which is just very simple. So with that, it's going to actually produce this representation, which is what we have here. So the hypothesis model is simply theta transpose times that of x vector, where the theta is a vector, is an m plus 1-dimensional vector. So this is how you would represent a multi-feature, multivariate linear regression model for the hypothesis. Okay, so what? So in this case, when you have an expanded version of that, then the question is, how do you define the cost function? And then, once again, how do you perform the gradient descent? So now here, unlike before, we now have m plus 1-dimensional vector for the parameter. And so as a result, the cost function is going to be not just 2-dimensional, but m plus 1-dimensional vector. So the j function, which is the cost function, then the format is about the same, but here, once again, this is going to be this here, the hypothesis function is right here, which once again, theta here is an m plus 1-dimensional. So with that, with this type of cost function, then the gradient descent is exactly the same as before. We just do the repetition of this updating procedure, and that updating procedure is exactly the same. That is theta j is equal to theta j of the previous plus the changes of the theta j. And this change then is equal to the negative of the alpha times the gradient of the cost function, where the cost function, once again, is m plus 1 dimensional vector. And then you do the gradient for each of the parameter, say, theta j. And we do this for simultaneously for all of the parameters, say theta 0 to theta 1, theta m. So now, previously with say n being, well, actually this is not n, but say m equal to 1, and so this is for the algorithm with m greater than equal to 1. So sorry about that, in the confusion in the notation. So m, we're talking about the dimension of the parameter, whereas n represents the number of the samples, right? Number of the samples. Okay, so for previously, when we had just m being equal to 1, this means that we only had the theta 0 as well as theta 1, right? So just two parameters. For theta 0, the update model is this, right? Whereas, for example, when you take the partial derivative of the cost function with respect to theta 0, we have this representation, which is multiplied by 1. For theta 1, the right-hand side becomes x1, right? So that's the difference. Before we had just 1 multiplied. Now for theta 1, we have the x1 multiplied. And we did this simultaneously. Now for the case of the m features, right, or multivariate feature, m greater than or equal to, say, 1, then we do exactly the same thing. We do the repetition of this update procedure, where by taking the derivative of the cost function with respect to each of these parameters, it essentially becomes this. You're multiplying everything, right? And then you're multiplying this by, say, x of j to the ith sample. For example, this actually becomes exactly the first one. So theta 0 is this, where theta 0 happens to be equal to 1 because we made that assumption, right? We made that assumption. So this, as you can see, is exactly same as this. And similarly for theta 1, this is going to become x1, which is same as this. For theta 2, it is then should be multiplied by the x2, which is associated by say theta 2. And similarly, you can carry on. So for example, say say theta 3. This is going to be theta 3 minus alpha 1 over n of the sum of the whole thing, which is this, and it is then multiplied by x sub 3 of the ith sample, okay, where each of the subscript represents the particular the feature, right? So for example, in the case of say vector x, where the vector x, the first one is equal to 1, but then say x1 could be that of, say, the size of the housing. So x2 could be, say, a number of rooms, and so forth. Okay, so you could have like multidimensional feature set, which is what each of these represents. Okay, so so this was pretty simple, right? So this was just an expansion of taking the gradient process and update each of these parameters. Okay, so now the question is, how do we do this? How do we carry out this implementation without confronting with any of the issues? Now, one of the possible issues is having to do with different scaling of the feature. For example, say x1 compared to that of x2. Say x1 is the size of the housing, whereas for x2 is the number of bedrooms. And as you can see, the size of the housing is from 0 to, let's say, 2,000. So value is very, very high, 2,000, versus, say, the number of bedroom. The maximum is about 5. So it's like stretching from between 1 to 5. So this means that when you do, in fact, say, plot out the cost function, looking at just two parameters, theta 1 and theta 2, it's going to be pretty much skewed looking like this. Which is going to actually affect, depending on the situation that you are in. But what it's going to do is that it's actually going to slow down the process of convergence if say the parameter theta 1 and theta 2 have a very different feature scaling. So what you do is that you can do the normalization either by normalization by dividing the feature by the maximum value, or you can do the mean normalization. That is, you subtract off by the mean, and then you divide by the, let's say, standard deviation. For example, so rather than having this type of situation, what you want to do is to have, say, theta 1 and theta 2 about similar values. So in the case of, say, x1, the way we can do that is to normalize it by dividing it by the maximum value, which in this case happens to be the size of the maximum. Size is about 2,000, so you divide by, say, 2,000. And similarly, the x2, which is the feature for the number of bedrooms, you divide by the maximum positive value, which is 5. So that means that, x1 and x2, typically the value is going to be somewhat between 0 to 1, right? So that's going to actually normalize the feature value, and then it's going to allow you to have a, say, cost function that is pretty much balanced in terms of the type of bowl shape that you have, rather than having very skewed bowl shape looking like this. So so there are different ways of scaling normalization, but what we want to do is that essentially we want every feature to be approximately between, say, -1 to +1. So assuming that the first value of x feature being equal to 1, which is assumed, then some of the typical ranges of the values would be, let's say, if x1 is, say, between 0 to 3, this is okay. This is also not too bad. But if it is very, very far away from, say, from -1 to +1 range, this is actually pretty bad, okay? And similarly, this is also not very good. This is okay, very, not too bad. This is also okay, not too bad. But if the feature value is just way too small or way too large, then they need to become, once again, normalized so that all the features be put in a range between -1 to +1. Another way of normalization is that we can replace x with say x with the subtracting off by the mean value, and then we can then divide by the possible maximum value. So for example, so x1 being, in order to put it, say, between -0.5 to +0.5, is that you can then subtract all by the average value, which is 1,000, and then divide by the maximum positive value, which is 2,000. And similarly, x2, which the number of bedroom, is subtracted off by the mean value, let's say being, let's say, 2, and then it is divided by, let's say if it is 1 to 5 possible bedrooms, we can then maybe divide by, say, 4, because rather than having the maximum value, you can then use the maximum minus the minimum value. So this is actually the maximum subtracted off by the minimum. So 5 is the maximum value and 1 is the minimum value. So the denominator here should be about 4. Okay. So you can actually do two possible ways of normalization. You can then use this transformation or this transformation. The numerator is the same. The denominator in the case of this normalization is that you use the standard deviation, or once again, just the difference between the maximum value to that of the minimum value. Okay, so the gradient descent, once again, is this. So you can then do the debugging. So here, what you want to do is to make sure that the gradient descent actually is working correctly. So one of the key elements in being able to see if the gradient descent algorithm actually does work correctly is to choose the correct or appropriate learning rate alpha. And so how do we do that? Well, the way we can do that is by looking at the the way how the corresponding say cost function becomes converged, or the rate of convergence. So for example, the cost function, as as per the number of iterations, should be actually decreasing for after each of the iteration. So this is something that you want to see whether or not it actually decreases by going through this iteration. So if the convergence actually takes place, which is right here, is when, for example, the changes in the cost function does not change very much. That is, if it decreases by say less than say 0.001 in one particular iteration at somewhere here, then we can declare convergence. The other thing is for example, if the gradient descent is not working, then the number of iteration actually diverges rather than converges. It should actually go this way, but if it goes upward, then it's a sure sign that the gradient descent is not working, or something is wrong with the implementation. And you could also have, once again, this type of situation. That is, when you could also have a non-convex situation with, say, not very smooth, error function, or the cost function. In that case, there are other ways of determining where the global minimum is, like the simulated annealing and other procedure. But we're not going to actually go through that process, because once again, the easiest solution for dealing with this type of problem is to make, rather than using the gradient descent approach, but using, say, artificial neural net or the deep learning model for, let's say, the regression. On the other hand, you could also have alpha being very, very large to rather than converge into a divergent situation. So in other words, we have studied here with alpha sufficiently small, it should actually arrive to the global minimum, where you have the convex situation. But if alpha is very large, it should actually diverge. So once again, alpha should be somewhat just about right. So the question is, how do we know if alpha is just about right? And I sort of said that if alpha is somewhere around say 0.1, I think that would be actually a good starting point for alpha. Okay, well, what I want to do is that I will just add the rest of the materials at the next round.